Now that we've looked at individual logic gates, you need to be able to deal with combinational circuits. So this is when you have more than one logic gate together. The things that you need to be able to do are write out the algebraic expression for the gate, draw the truth table, and work out if there is an equivalent circuit. So, for example, I'm always using A and B as my inputs, and Q is my output. So this is a very simple example. Here I have a Nand gate. I know that it's Nand because it's got the shape of an AND gate and it's got the inverter circle on it. So A and B, draw my combinational AND, A, B, and then my line across the top because I have knotted my AND gate. And then it goes through this, and this is a NOT gate, so I end up with an A, a B, knotted, going in as my input, and coming out, I knot it twice. So I actually have Q is equal to A, B, not. If I draw out my truth table for this, so A, B, you have to break this down into steps. So my first step is I AND it, and I get 0, 0, 0, 1. My next step is I take my A, B, and I knot it, and I get 1, 1, 1, 0. And then my final step is A, B, not. And this takes me back. You can see here that AB and AB not is the same as they're the same as each other. So actually, if you knot anything twice, it's equal to this. So you can say that Q is equal to A and B. So the equivalent circuit would just be an AND gate. Let's quickly have a look at another example. So again, in this case, I've got two inputs, A and B. I've got two logic gates, and they're both NAND gates. So here I'm going to have A and B knotted. And this shows you here, I've actually got this, so I've got two inputs, but they're both the same because the output of this one is splitting into these two inputs. So I've got A and B knotted and A and B knotted as the two inputs. So here I have A and B knotted and A and B knotted, all knotted. So the dot here represents that they're ANDed together, and the whole thing is knotted. So this is my algebraic expression for my output function Q, and my truth table will look like this. I need to break this down into steps. So you know what the truth table looks like for A and B. Then not A and B is going to be this. Then if you AND this with itself, well, it's just going to be equal to itself. Anything ANDed to itself will be equal to itself, because if A and B knotted and A and B knotted, they're always going to be the same. And this one finally is going to be the inverted of the previous function. So we've found that this is equal to the same as AB, because you can see that these are actually the same as each other. This one here and this one here are the same. So the equivalent circuit is just another AND gate. In order to be able to understand and simplify more complicated combinational circuits, you need to be able to understand the rules of Boolean algebra. It looks like a long list, but they're really similar to normal algebraic rules, and I'm going to go through them so that you understand what's going on, because this is a list that you need to know. It won't be provided in the exam. So to start with, if you have OR functions, The order doesn't matter, so A or B, it doesn't matter if it's B or A, so that should be fairly straightforward. It also doesn't matter if you have done, if you've gone through, so the brackets denote that you've done this first, so you've had a B or a C and then you've ORed it to an A, so this would be exactly the same as having this, so the order doesn't matter here. And brackets, if you end up with brackets in your expression, you treat them exactly the same as you would in a normal algebraic expression. So here I can multiply the A and the B, and then I can multiply out the A and the C. So even though this, it's not a multiplication, it's an and. So I've got A and B or C. So that's the same as having A and B or A and C. So these rules all apply. And similarly, the AND rules, if I have A and B, that the order doesn't matter, so it's the same as having B and A. And finally, again, similar to this one, if you have brackets denoting that you've done something first, so if I've done B and C, and then I AND it to A, that would be just the same if I had A and B and I ANDed it to C. So hopefully these rules will get you going in terms of being able to simplify expressions like this. Then there are some other rules that you need to know. So we'll start with the ones for OR. So in this situation, you can either think it through logically, what would happen if you had A or 0. So you can think that through logically, and well, if it's A or 0, it's always going to be equal to A. If you're struggling to get your head around that, then what you can actually do is draw out a sort of truth table, right? So you can write out, well, what is A equal to? What is 0 equal to? What is 1 equal to? And here we're also using not A's. So A, it's possible for A to be 0 or 1, but 0 is always 0. So in this case, if you have A or 0, well, that's always going to be here, that's going to be 0, and here that's going to be 1. So it's going to give you the same expression as A, so you can work it out that way. In this case, we've got A plus 1. 1 is always 1. So A or 1 is always equal to 1. Okay? And I'll continue to go through this. So A or A is always going to be equal to A, and A or not A is going to give you 1, because not A is the opposite. So if you have A or not A, well, you've always got a 1 in one of these. So those are your OR expressions, and these really help you to simplify the situations when we have more complicated algebraic expressions. And then finally, the other rules that you need to know are the AND rules. So we have A and 0, A and 1, A and A, and not A. So we can use the same table, of course, and you should find, A and 1, A and A, and A and not A is never going to happen. There are just a few more complicated simplification rules that become really useful when we have more complex mathematical expressions. So you still need to keep these in mind to be able to simplify, but I'll just introduce these extra couple of rules that are very helpful. So A plus AB, something you can do to simplify this, you might think it already looks simple, but actually if you were to take the A's, so both terms have A in common, if you take the A's out, you end up with 1 plus B. So A or A and B is the equivalent of A and 1 or B. Well, we know that if you have B or 1, that's going to be equal to 1. So then you have A and 1. Well, A and 1 is always going to be equal to A. So this expression here is equal to A. So this rule is very useful later on. I'll show you another example where you can start using this one straight away. So another example, a plus not a, b. If we want to simplify this, well, this time I don't have a common term. But actually, if I use this rule that I just introduced, that I just proved, I can write a in terms of this here. And yeah, this doesn't look like simplification, right? Because it actually looks like I'm making it more complicated, but it drops out nicely. So if I use this and substitute a here, then I end up with a plus ab. So I write that instead of a, plus not a, b. Okay? Now what have I got? Well, now I've got a common b term here. So I can write a plus b, a plus not a. So a or not a is always going to give you 1. So I end up with a plus b, 1. So this is equal to a plus b. So you can see that this rule is really helpful, and we've shown that this expression is equal to this expression here. And this is the last example I'll show you where you can implement these rules that we've already gone through. So a or b and a or c. So we start off by multiplying out our brackets. You know that a and a is going to be equal to a. I just find it neater to write everything in alphabetical order, but you don't have to. Here, we can apply this rule here. So we had a or a and b was equal to a. So this is going to give you the same situation. So this thing here is going to be equal to a. Then here we've also got this same situation where we had a plus ac, that's equal to a, but a or a and b is also equal to a. And that's as simple as this solution can get.